Hello, I'm John Plesger from Team Thermos, and today we're going to walk you through the preliminary design of our residential-sized solar thermal power plant. Currently, the only solar thermal in use on the consumer scale is used for heating water or heating a living space, not for the generation of electricity. By using a microturbine, we hope to expand the use of solar thermal by implementing a design that can provide power 24 hours a day and will compete with and complement solar photovoltaics. The team has combined 52 years of professional experience along with a broad spectrum of knowledge in the electrical engineering field. This has helped keep our goals grounded, which has led to many pivot points in the process and changes in the design. Before we dig into the details of our design, I'd like to have the team tell you a little bit about themselves and introduce you to our professional mentor who has been a steadfast guide to us along the way. So, without further ado, here's David to start us off.
Hello, my name is David Mummy. A little about me. I've been an electrician in the Air Force for the past 10 years, dealing with everything from high voltage base distribution all the way down to fire alarm control panels and everything in between.
Hello, I'm Chris Jones. I'm an ETCP certified entertainment electrician working for IATSE Local 504 here in Southern California. I've been working with electrical components and automation for an excess of 20 years.
Hello, my name is Michelle Tidwell. Academically, I've studied electromagnetics and silicon devices as my main pathways. I have 16 years of experience as an electronics engineering technician in the engineering aviation field, working with different types of information management and networking systems. I would also like to introduce Team Thermos's mentor, Tom Potts. Tom has been in the electrical engineering field for 32 years. Tom has a broad background in engineering. For example, working with instrumentation and testing of liquid-fueled rocket engines to the design and development of flight-critical military and commercial avionic products. Tom brings great insight to our team from the industrial world, along with his academia work in high-reliability space research instruments.
Which brings us back to me, John Plesger. I found myself fortunate to work with a group as experienced as this one. I don't have the years of professional electrical related experience, but I've worked as a wildland firefighter for many years, where I've picked up many unique problem solving and communication skills. At ASU, I have focused my education in power systems. Now that with everyone introduced, we can dig into our presentation. First, Michelle is going to go over the inspiration behind our idea. David will then review the market research we performed that helps solidify our goals. Chris will give a brief overview of the design, and I'll discuss the goals we hope to achieve. We'll then take a step back and discuss the innovations and technology that our design is building off. From there, we'll take a deeper dive into our design, how we plan to split up the work, and discuss some potential obstacles we foresee.
Thank you, John. The simplest observation of extremely hot asphalt in the southwest US and some background knowledge on thermal power plants, specifically low thermal gradient power plants such as ocean thermal and geothermal, inspired this idea. Due to the recent natural disasters and rolling blackouts, this became an idea that was easier for us as a group to rally behind. David, how about some market research from our survey?
According to Team Thermos's market research, 92.5% of participants stated emphatically that the world needs to begin using renewable electrical energy sources at a much higher volume. With the strain on the electric grid, making rolling blackouts necessary in California, as well as a rising impact of global natural disasters, consumers of electricity need scalable and affordable means of providing power without total reliance on the national electric grid. From the same group of market research participants, a staggering 66.7% do not currently have such a system installed. While the environmental concerns drove the desire to install these systems, cost was identified as a major impedance to a wider scale employment of renewable technology.
Our plan is to design a solar power plant that can be scaled from a rooftop to a parking lot. The plant would be built to complement or compete with current solar photovoltaic technology. Our design incorporates a black body collector that will be used to heat a working fluid in a small-scale power plant. The power plant would be cooled by means of a geothermal ground loop. We have collected solar irradiance data in the southwest United States and have deployed a small sensor package to the other team members' locations. This data collection will help us determine what area could be best served by our design. Our goal is to achieve the same, if not better, performance than a PV system.
Thanks, Chris. We have 4 main goals for this design. First is sustainability. This is easily met since we will be generating electricity from solar, a renewable source. That said, we would like to use components that have a long lifespan in our design, ideally 20 years. This will bolster our commitment to sustainability. The second is size. We want our design to function with a solar collector size of only 1.6 square meters. This is comparable to that of a residential solar panel. Ideally, we want our entire plant design to fit within a combined 17 square meters, about the size of an average parking space. This would optimize the design for consumer use and distributed energy generation. Our third goal is to design a power plant to be able to financially compete with available residential photovoltaics on the market today. These can produce electricity at an average of 8 cents per kilowatt hour. We'd like our design to meet or beat that generation cost. Finally, our most basic goal is to design something that can produce 1 kilowatt of power. This design is only possible due to the innovations in power generation. We'll now quickly review these background to give a better understanding of our own design.
There have been several attempts to make solar thermal energy viable on an industrial scale. Solar 1 and Solar 2 in the Mojave Desert of California and Gemma Solar, located in Andalusia, Spain, all produce electricity by focusing the sunlight onto a tower and heating a working fluid. There are major environmental consequences with this design. One major issue is the amount of ground area required to host these types of systems. Nevada Solar 1, Solar Energy Generating System, also known as SEGS, in San Bernardino County, California, and Valle Solar in Katy, Spain, are examples of a slightly different method of collecting solar thermal power. They use parabolic mirrors to reflect sunlight in order to heat a pipe of working fluid. Another interesting research venture is the eHub project. Here is Chris to give more details on that.
The eHub project out of the Netherlands has taken a different approach to solar thermal. In their design, they intend to use a blacktop roadway to collect and then store thermal energy underground. This energy can then be used later in the winter months for district heating. Their local research has determined that a roadway surface has an average increase of almost 60 degrees Fahrenheit in direct sunlight. This small thermal gradient led us to look at other forms of low gradient thermal processes, like Hawaii's Makai OTEC plant and the Unterhaching geothermal plant in Germany. John, what are some of the details of those two plants?
Both plants can produce energy from a small thermal gradient by using an organic working fluid that has a lower boiling point than water. For example, Makai's ocean thermal plant uses ammonia as a working fluid, which has a boiling point of negative 28 degrees Fahrenheit. The Unterhaching also uses ammonia. However, instead of the normal Rankine cycle, it uses the Kalina cycle to further boost the energy from a low temperature thermal well. The Kalina cycle differs in that it utilizes the waste heat from the exhaust of gas turbines.
Up until recently, the waste heat from small power plants and engines was just that, waste. Only the larger plants could efficiently produce power from their exhaust. That was until the invention of microturbines. Now almost any heat source can produce energy from a microturbine. These microturbines can range from 1.5 kilowatt green turbines from DeepRog to the larger 215 kilowatt microsteam from Energint. These turbines have been installed in applications ranging from commercial buildings to cargo freighters. We plan on using them in our plant design, where our working fluid will be heated by means of a solar collector. For some history on solar collectors, here's David.
From the late 19th century, when a black cistern would have been warmed by the sun, to the technology of the 21st century, hot water producing solar thermal collectors have been widely available for centuries. There are 3 main methods to heat water from a collection of solar energy: a glazed solar plate, an unglazed solar plate, and evacuated tube designs. Unglazed solar plates are generally used for low thermal loads, while evacuated tubes and glazed solar plates are used in hot water systems. Flat plate solar collectors use a series of tubes to transfer the heat energy collected on a dark surface, while evacuated tubes heat a working fluid inside of a tube coated in absorption material. In addition, there have been recent developments that marries the two technologies together, evacuated flat plate. The evacuated flat plate is a more efficient method in cooler climates where the heat load is high. In comparison, commercial power plants employ a parabolic trough and point focus methods. The parabolic trough method heats a pipe of working fluid as it reflects the sun off an arc reflective media. Point focus either focuses light energy onto a tower or can have a source a few meters in front of the reflector. Both point focus and parabolic trough gain efficiency by being able to track the sun.
As mentioned before, we will be building a small-scale solar thermal power plant. The team broke out into two subsystem teams, the simulation team and the feedback system team, to better utilize the team's knowledge and resources. The goal of the simulation team is to design and simulate the power plant and condenser portion of the solar thermal power plant. The goal of the feedback subsystem team is to adjust the evaporator fluid flow per the feedback temperature sensor readings in the working fluid loop in order to keep the system operating at the optimal energy transfer. Here is Chris to explain more on how we plan on accomplishing this task.
We plan on purchasing a pre-made solar thermal panel to use as our black body. Using a custom-designed low-side pump driver, we will pump a fluid through a heat exchanger and then the collector. This fluid will be pumped at a variable flow rate that is determined by the current temperature of the working fluid. This will be done to try to maintain a constant ideal temperature of approximately 120 degrees Fahrenheit. The fluid in the evaporator loop will collect in a thermal vessel until it is needed. This thermal vessel will also have an option for a secondary heat source like natural gas or heating oil. From there, we plan on simulating the internal plant, including simulating different working fluids and the addition of the Kalina cycle. We will also be simulating a ground loop cooling to condense the working fluid in the plant. The ground loop uses a well or in-ground cooling loop that will remain at an average temperature of 55 degrees Fahrenheit. Through using our evaporator design and simulating power plant, we hope to achieve a net 1 kilowatt from the system.
We plan on using the parameters and data from our hardware build into the software portion of our design. We are looking at using EcoSim Pro, which is a software package that has organic Rankine cycle, Kalina cycle, and solar thermal toolboxes. That package was quoted at $10,000, however, so we are working on either sharing a license with the ASU School of Sustainability or developing our own simulation with Simulink. We as a team have firsthand felt the effects of climate change while also having a finger on the growing pulse of the renewable energy market. This drove our discussion of a project to focus on a main goal of sustainable energy generation. By looking in the past forays of low thermal gradient energy generation while keeping eyes to the future, we believe we've presented a design that can competitively generate renewable energy.